Well, it looks like we have a good crowd here, so let's go ahead and get started, guys. So my name is Jeff Hoyle. I serve as the Director of Ergonomic Services for the Ergonomic Center, which is part of NC State University. Just want to say welcome, everyone. Thanks for joining us for our first webinar in our Ergonomics Solution webinar series where we're going to be talking about casters, right? A pretty common solution. So I know there's some out there, and and I've certainly seen it firsthand that if they've put some wheels on it, okay, all the problems have gone away and the lifting and carrying issues have now been resolved, right? Well, that's not necessarily the case. And I know that or I should say, know that all casters and wheels are not created equally. And there's actually quite a bit of science behind casters and cart design. So, joining me today to help educate us and unveil some of this science is Doug Backinger, who is the VP of Solutions and Innovation at a casters solution company called Caster Concepts. Many of you have maybe have probably heard of them before, or perhaps have worked with them. But before I formally introduce him, just want to help the audience know who we are as an organization and go through just some quick logistics before turning things over to Doug. So, Doug, since you're presenting, if I could get you to jump to slide 2. So just to give you a quick background about the center, we were founded back in 1994. Just celebrated our 30-year anniversary last year. So originally we were part of North Carolina Department of Labor, so our mission was just within North Carolina. However, since then, and for quite a number of years, our outreach has spread across the United States and even internationally. So I will say the vast majority of our work is still here within the States, but we are a not-for-profit organization, again, part of NC State University. We're actually housed within the Department of Industrial and Systems Engineering. So I think there's often maybe a misconception that we just do research and are removed from the real world. Well, honestly, that really couldn't be further from the truth. Again, our mission is really just outreach to business and industry to help them create or enhance their ergonomics initiatives internally. So, we do that primarily through consulting and training services for companies and on occasion through some applied research projects. So you can certainly find out about more about our organization at our website at ergocenter.ncsu.edu. If I have you jump to the next slide, Doug. Obviously, as you know, as part of the university and our center, our mission and our purpose, and especially with this webinar solution series that we're launching, this is our first one, is to provide education and outreach to companies, again, to provide them with expertise to improve their internal ergonomics culture, to improve the well-being of their people, and help companies really optimize their business and positively impact their bottom line. So basically, we help companies protect their people and their profits. Next slide, as far as webinar logistics. Um, so this webinar is being recorded, and the link will be sent out to all you guys as registrants at a later date, so you will have access to it after the fact. We have muted the audience during the webinar just to eliminate any background noise or interruptions. But certainly, if you have questions, please enter them in the Zoom chat, which you should be able to access at the bottom of the panel in your Zoom window. So we will take some questions at the end, and I'll try to help facilitate that. Doug, if you just jump to the next slide there. So Doug and his team have titled this presentation "Saving Backs and Bucks: The Importance of Ergonomic Casters," which is, I think, quite suitable for our topic today. If you jump one more, Doug, I'll just formally introduce you. So yeah, just to formally introduce Doug here, we're really fortunate to have him with us today from Caster Concepts. He's certainly a wealth of knowledge, but he comes to us again as the VP of Solutions and Innovation with a lot of experience, over 17 years in the caster industry, and has a pretty extensive educational background. He's one of us. Anal engineers, which I can say that because I'm one myself, but does have a bachelor's in mechanical engineering and a master's in manufacturing engineering, both from University of Michigan, which is a great school. Even though I had to give them a hard time since my master's in industrial engineering was from the Ohio State University, so a little bit of rivals there, but
Won't
but
hold it
both.
against you.
That's right. But both have really good engineering programs, and certainly they do it at U of M. Um, so I know their company, and he specifically really prides himself on customizing solutions to client needs. So with that, I'll turn things over to you, Doug, and thanks for joining us today.
Yeah, absolutely. Thanks for having me. Jeff and Julia, thanks for reaching out and let me be the first speaker here in this series. So I'm excited to do that. And I'm also excited to educate people on casters and the impact they can have. Just because normally casters are the last thing people think about, and then they get them on, they get a cart out on the floor, and then it doesn't work the way they want it to. And now they're trying to scramble and come up with a less optimized solution. And I guess just to touch more on my background, where I think I'm unique in this industry, so spending the first third of my career doing product design and product testing, I think gave me, I got to see a lot of what worked and what didn't work from a product design standpoint. And then moving into operations, finding out how to make things cost efficiently, and now being more on the customer facing side and getting to see all the challenges that the manufacturers face, with material handling issues across the US, I think is, given me a broad experience of different solutions and what's worked and what hasn't, and things that manufacturers tend to struggle with. So with that, I'll give you a little bit about Caster Concepts. So we're about 40 years old, located in Albion, Michigan. So for people that aren't familiar, I'll give you the mitten, and we're about right there, South Central. So we have our factory there, about 90,000 square feet, make everything in that factory. So where we're different than other caster manufacturers in the US is we really pride ourselves on developing optimized material handling solutions. So not necessarily whatever's in our catalog, but being able to tailor that and customize those products and do it in a fast and cost efficient way. So we're really not constrained by, oh, well, this is the only thing we have available. We can really look at your process and come up with an optimal solution and give you that quickly. So again, I'm the caster expert here. I'm not the ergonomics expert, but just to kick it off, from the Material Handling Institute, what is ergonomics? Ergonomics is the science that seeks to adapt work or working conditions to suit the abilities of the worker. So what that means to us, being in material handling, is how do we take a cart, dolly, anything that moves in a factory and make it safe for somebody to move, make it efficient in production, and make sure it's durable enough where it's not breaking down, and you're getting more than the lifespan that you think you should be getting out of it. And again, as it comes to ergonomics and material handling, there's a lot of data out there, that says, a wide variety of numbers, where overexertion injuries are costing manufacturing companies billions of dollars a year. And whether you argue a back or shoulder injury is 40 grand or 100 grand or more than that, it all comes down to it's a real cost to manufacturers, and they're committed to doing something about it and making their work environment safer for their employees. You know, we initially started to see push force standards come out probably 15, 20 years ago, and that started, I would say, in heavily unionized automotive facilities, where now we're seeing it across all industries, small companies, medium-sized companies, large companies. They're all realizing the value of their employees and what that means to keep them safe and happy on the job. I mean, one, people are hard to find, so the people you got to keep them productive. And two, I think we've seen some changes in the industry over the last few years that, know, maybe 20 years ago they were moving 1,000 pounds. Now we're talking about moving 2,000, 2,500, 3,000 pounds safely with one person and have them do it multiple times in a shift. So a lot of this is driven by EVs. These batteries are heavy. They need to pack a lot of them onto a cart to be efficient. So we'll talk about that in some case studies at the end of this, just so you can kind of see how we go about solving some of these issues.
And if I could, Doug, just to chime in here, I think a lot of people think, okay, there's lots of risks involved with lifting, right? And lifting typically puts more compressive loading on the spine. Whereas pushing and pulling, right, actually puts shear forces on the spine, right? And actually your spine is weaker in shear forces, right? Where you have forces acting more, linearly on the vertebrae and on the discs, versus lifting is more compressive forces. So, you do have to protect your people with pushing and pulling, obviously, and casters is one way to do that. So just wanted to point that out.
Yeah, thanks, Jeff. So a lot of what we see in industry comes from the Liberty Mutual, the Snook material handling tables. And just to kind of lay this out graphically, if you're in a manufacturing operation and you're continually pushing a cart that takes 70 pounds to get moving, that's going to be safe for maybe 38% of your population, a very small percent of your population, where a lot of your workers will be at risk of an injury. What we see in industry is a lot of standards in that 50 to 40 pound range. And you can see that there's quite a big jump getting to 50-pound starting push force. And, that gets you up to around 80% safety rate. Whereas if you can get to 40 pounds, now you're upwards of 90%. Whereas kind of what I'd say is the lowest standard I've seen is 33 pounds. So for the most part, everyone's in that 40 to 45 range. There's a few up closer to 50, and there's even a few then down in that 35 range. And again, it's all about how do they reduce the risk of injury in those material handling operations. So now we'll talk about the different parts of the caster, how they affect starting forces. And really, I'm going to focus on starting forces because normally your sustained forces are so much lower than your starting force. So if you can keep that starting force in that safe range, normally your sustained forces are going to be much, much lower, like less than half of that starting force. So a lot of what I'm going to talk about today is that max push force. So the things that we're going to talk about as it relates to a caster. So we'll talk about the swivel section design. So what actually makes it pivot and spin. Um, we'll talk about the wheel design. So how that looks size-wise, different profiles, different materials for the wheels, as well as then once you kind of optimize the caster, how do you actually put them on a cart in a way that minimizes push forces? So swivel section designs on casters. So there's really three main types in industry. So with the initial kind of a first technology of casters, this kingpin style caster, where you have a bolt running through the middle, if you can see my mouse, which then you have two rows of bearing elements. So one main load bearing and then a thrust bearing beneath that. And then you either tighten this all together, with a nut or some other fastening device, or with some of the lower end casters, this all tends to be like cold stamped and then pressed together. So with the first design with a nut where you tighten everything together, you end up preloading the bearings. So you're actually adding drag to that swivel section. So while it's a nice swivel section in terms of, robustness and durability, you know, when you're looking at trying to reduce push forces and improve rollability, adding that extra drag really doesn't help. And then on the lower end, when you have the all pressed together swivel section, it's not very precise. It's really not heat treated. So you end up with a somewhat loose and sloppy design that again is just hard to spin. So, these are still used in industry today. Good swivel sections, just definitely not the choice for reducing push forces. So the second design that came out, and I believe this was in the 1960s or 1970s, is this kingpinless design where they've eliminated the kingpin, so you remove a point of failure. Um, maybe closer to a ball bearing type design today, where you're machining your own bearing raceways, heat treating steel, and then welding components to it, legs, top plates. So again, a very robust swivel section design, easier to rotate than a kingpin style caster. But where you have drawbacks here is you're creating this bearing raceway and you have to do it in a manner that you can still weld to it. So you have to choose a grade of steel that you can weld to. You have to then heat treat it. So you can't really heat treat it too hard or else you're going to make it too brittle to weld to. And then just with machining tolerances and whatnot and warpage during welding, you end up with a fairly loose swivel section. So if you guys have seen these out in industry, normally you can pick them up. There's some play back and forth. We actually have a caster standard called the ICWM spec. It's an ANSI standard, that sets limits to the amount of play you can have in that swivel section. So again, it works better than a kingpin, but still not really optimized. So the last type of caster swivel section that's been around now, maybe close to 20 years. So maintenance-free designs. So these actually use a separate bearing structure. So in this case, a ball bearing that's sealed. And in this case now, since you're using a separate bearing and not welding to it, you can optimize the grades of steel. You can optimize the heat treatment. Uh, you can precision grind the raceways. So now all of a sudden you have a bearing element that's much tighter and much more precise that allows for easier rotation. So then with the way the caster's designed, that's all pressed together and that will have the least amount of force required to start to rotate that swivel section. So now that I've covered kind of the different swivel section designs, the next major part of your caster rig that's going to determine how well or determine how low you can get your push forces is your swivel offset. So if you take the center line of your swivel section and then where your wheel's located, that offset distance is what we call swivel lead or swivel offset. So I know this can be a somewhat confusing topic because most people say, oh, well, extend the swivel lead out as far as you can, and that's going to reduce the amount of force it takes to get that caster to rotate. And theoretically, that's true, right? I mean, you have a much larger moment arm.
Yep.
You can apply a much lower force to get the same amount of torque. The issue is as you extend out that moment arm, you're now putting more and more stress on that swivel section. So what we found in our testing is it's actually more of a parabola, and there's an optimal point for swivel lead, which if you go past it, then your push force starts to, well, I guess, increase again. So don't just assume the longest swivel lead is the best. Each swivel section design has an optimal lead, and those need to be tested for and determined, by the manufacturer on what that should be.
Sure. And I will say, as far as the clients that we typically work with, I will say most of their carts, they don't have routine preventative maintenance on them, right? It's not like it's an annual thing. So usually the only time that they may change out casters or check them or lubricate them or make sure they're free of debris is when somebody reports an issue, right? So I think everybody's probably interested in the casters that would give you the least amount of maintenance, right?
Yeah, yeah. So that's a good point. I'm glad you brought that up. So with the maintenance free swivel sections, to your point, I've been in hundreds of different facilities, and I can count on one hand the number of places that actually have a PM program where they actually grease casters.
Right,
Everyone else is like, "Oh, I didn't know I had to do that," and then they wonder why like they don't rotate anymore.
right.
So, so that is a nice point about the maintenance free casters is you really don't have to do anything to them. And we're running tests, internal tests now, just to show how much more life you get out of them compared to traditional swivel sections. So where, day one, you might pass your push force, like with a kingpinless style swivel section. 1 year later, you haven't greased it, you haven't done anything to it, it kind of follows the same path, so it's worn down a little bit. You're probably not going to pass your push force anymore. Whereas what we see with the maintenance free is you're extending that life, 3 to 5 times longer, and you can get the same performance on year three that you did on day one. So there are other benefits to the maintenance free swivel sections too in terms of life and longevity.
Gotcha.
Now, I guess the downside to it is, where the other ones can take a lot of abuse, because they aren't super precise. The maintenance free don't do as well in really abusive applications where you got a lot of forklifts or loads dropping onto carts. But certainly in most ergonomic applications, like they're more than enough.
Trade-offs.
All right, so moving into wheel designs, and this is really where you get into trade-offs. So like any good engineering problem, you optimize one part of the design and you're going to trade off something somewhere else. So, think about wheel diameter. Simple physics tells you the larger the diameter of your wheel, the easier it's going to be to get that to start rolling. Now, if you think about that from a manufacturing standpoint, you're like, well, let me just maximize all my wheels. I'll make them 24 inches in diameter, and this thing's going to roll super easy. Well, except now you're putting them on carts that people are usually working on or picking parts off of, and you need to keep that all within a certain working height to make it ergonomic for the employee working on the cart. So you really can't just make the wheels as large as possible, that you have other design constraints within the cart. So usually what we see is, wheel sizes between 6 inch diameter to 10 inch diameter, and which results in a caster overall height of, 7.5 to 12.5 or so. So then, we're kind of limited on wheel diameter with the sizes to keep things in a working height. So you say, okay, so what can I do to the width of my wheel to try to lower those push forces, improve my rolling resistance? So this little graphic here, what I'm trying to show is, so the wider the wheel, the narrower your contact patch is going to be that's in contact with the ground, right? Because again, it's force over area. Your wheel's going to deform some. So the wider you can make that, the narrower that contact patch is going to be. Now, this is really good for getting the wheel to start rolling, right? To think about like you have just a little bit of a lever that you try to get the wheel over to start rolling. The narrower that patch is, the easier it's going to roll. Now, the downside to that is with push forces on carts and where you get that maximum reading is really when the swivel casters swivel around. So now if you have a really wide wheel and you try to you know push that cart and get those casters to swivel, what you're going to have is now you've actually increased your push force. So again, wide wheels in a straight line, easy to roll. Wide wheels on a caster where they have to swivel, you're going to scrub that tire and it's going to increase your push forces. So then you're like, okay, so you tell me a large diameter is good. You tell me a wide wheel is good to a certain extent. So how do you combat some of these trade-offs? Because obviously you can't go too big, you can't go too wide. So that's where you get into the actual style of wheel in the wheel design. So, you just have normal flat-faced or slight crowned wheels. So again, it'll give you a narrow contact patch. but when it comes to swiveling on the caster, you're going to increase your push forces. So the balloon tread wheels, which I think people commonly see them as ergonomic wheels. So that's really only true with the right urethanes, because again, that balloon tread profile, you end up with, kind of a bigger footprint on the floor, so it's harder to get it to start rolling. But then, it's a fairly narrow section of the wheel that's in contact with the ground. So when it rotates around on the caster, you actually gain benefit there. And really the most ergonomic type that's been around now for maybe 10, 12 years are these split wheel designs where you have a wheel broken up into, say, two or three different segments, each with its own bearing that are all pressed together that can all rotate independently. And what this allows is you can now have a really wide wheel, and as it swivels with the swivel section, it doesn't really scrub on the ground anymore. You have each of these sections of the wheel that can rotate independently, and you really reduce that scrubbing force. So now, with the split wheel, what we call our Torgo, um, you can now have a wide wheel to get a narrow contact patch and still minimize those push forces because now you've reduced that scrubbing effect of a wide wheel. Okay, so wheel tread materials. So again, I like to call this the Goldilocks principle. It's not too hot, it's not too cold, it's just right. So in this case, the harder the wheel, the easier it's going to roll. Again, same principles. If you have a steel wheel, it's really not going to deform at all. You're going to have a really narrow contact patch, and it's going to be really easy to get that wheel to start rolling. If you even think about it from as the swivel section rotates, it's steel, has a low coefficient of friction. You're not going to scrub it as much either. The drawback to having a really hard wheel is it's going to tear apart your floors. You're going to wear ruts into your floors. You're going to take chips out of it. So again, you could minimize your push forces by having a really hard wheel, but now you're going to have another trade-off with how often do I want to replace my floors? And I have not talked to anybody yet that says I'm okay with replacing my floor yearly. Like they want to protect that thing almost, I won't say at all costs, but they want to make sure that floor lasts for 20 years plus. So next year's like, well, let me go to the opposite side and I'll go with a rubber wheel. I mean, just like we talked about on the slide before, rubber tends to be too soft. You get that wide contact patch. It's hard to get it to start rolling. It's hard, it scrubs a lot on the ground, but it protects your floor. So really what we found is urethane tires in the 85/8 and 95/8 durometer tend to be just right. So soft enough where it's not going to destroy your floor, but hard enough to still give you good rollability. And then when you're talking about urethanes, I mean, there's hundreds of different types of urethanes. I mean, we're always testing new urethanes in terms of, on our dynamometer, and then for push testing, you have different types that have different properties. And what we look for with an ergonomic urethane is something with high rebound. So think about rebound as like a bouncy ball, right? You drop that ball from a certain height, you want it to get as close back to that original height as possible. That means it's returning as much energy as possible. So the higher that is, the better. It's never going to return all of that energy, right? Because it's inelastic. But again, materials with a high rebound tend to perform well. And then you also need a blend of high tear strength because you need a tough material because you're on a manufacturing floor. You're going to run over debris. You're going to have stuff get in the way. You can't have it just grind itself to dust every time the wheel swivels. So you're looking really for two primary properties in high rebound and high tear strength. But then, when you look at the most ergonomic materials, so in our case, we color it green, you know, really good rollability, pretty tough material, but we know in certain applications, like it's not going to last that long, and you need to go to a tougher material. So we'll make trade-offs there and go to something with it's still ergonomic, just not as good, but it's way tougher. So that's where it's really not just, oh, here's the best urethane. It's always a trade-off of properties and evaluating the manufacturing environment and what that wheel is going to have to do and overcome every day to determine what's going to be your best material for that application.
Yeah, I know for me, I've always had confusion between, recommending phenolic wheels over, urethane wheels and the trade-offs between the two. And I guess your answer to that would be it depends on the application, I
Yeah.
guess, right?
Yep. Yep. So like phenolic or like nylon wheels. So again, from day one, they'll give you great performance from a push force standpoint. If they only get used a few times a week, they're really not towed around, there's really no debris on the floor, it's probably your best option. But as soon as you start to take a chunk out of those wheels, or they run over a piece of debris and it embeds in the wheel, now all of a sudden you're nowhere close to that initial push force reading. And that's usually what we see in industry is they'll use phenolics or they'll use nylons
Mhm.
as, for
Like
applications that,
gold standard or something, kind of.
well, but like it's a clean environment that they don't move that often. So they don't really have to worry about wear to the floors or, chunking out the wheels or anything like that. But high usage, like things that are getting towed around a plant, like that'll be urethane all day. All right. So now that we've kind of optimized the caster design, how does that play when you actually put them on a cart? So we see two main types in industry. So the first one being four-wheel caster steer. So you have two fixed or two rigid casters in the back, and then two swivel casters in the front. So this style is good because you can tow it around the plants, pretty versatile. Um, the bad thing about it is all four casters touch the ground. So you'd still have to fight two swivel casters rotating as you push this cart around. But again, that's probably the most common style that we see. The other style would be this diamond style where you have two rigids in the middle and then a single swivel on the front and a single swivel on the back. So we see two types of these. Either all four casters are touching, so you have the same drawback with the four-wheel caster steer, in that you still have two swivel sections to overcome. And then we also see a tilt style. So that would be where the rigids are slightly taller than the swivels. And what this actually allows is sometimes you can go with a bigger wheel for the rigid than you do for the swivels and take advantage of that extra size to reduce push force. And also by having that tilt, you really eliminate well, not totally eliminate, but greatly reduce the impact that the swivel casters have on your push forces. So I'll show you a case study here shortly where, on a tilt style setup, you can move a lot of weight and do it, with one person safely just by tweaking those rigid casters in the middle. So again, from our testing, it shows that a tilt style is always going to be the lowest in terms of push forces. You just have to decide in your application, can I handle being able to kind of teeter-totter back and forth a bit, or do I have to have everything on the ground and stable?
I know I've seen, personally, I've seen a specific application where it was a very heavy load and a very wide, like long load that was on a cart like that. And obviously
Yep.
the middle casters were larger in diameter, so you had the teeter totter kind of deal, but it moved incredibly easily,
Yep.
right? With such a long and heavy load. So good.
Well, just happened to be the next slide here.
Okay.
So this was a tread cart for a tire manufacturer, and it weighed 3,500 pounds. So they had it in a diamond style setup, tilt, and it required over 200 pounds of push force to get this thing to move. Like they actually sent this to our factory, and I think we had like 8 guys try to push this thing into position so we could try to do some testing. Like it was a nightmare. they required four people to move it, which I'm sure they were using more because again, this thing was just too hard to move. So again, using our design principles, when we looked at this, we said, okay, so it's a tilt style. So we know the swivels, like, I mean, they can't be terrible, but you don't have to fully optimize the swivel. So let's focus on the rigids in the middle and let's see if we can optimize those to be able to reduce that push force. So in this case, what we did was, I think they came in with 10-inch wheels. We had enough room to go up to 12-inch diameter. So we increased the diameter of the wheel. We also used, so our green urethane, so our most ergonomic urethane to get the best rebound. And then we said, okay, so now we know we have this contact patch we have to overcome. So can we spread out the number of wheels in contact with the ground to make that contact patch as narrow as possible? So we actually added two more rigid casters to the middle, which you can kind of see here. So now there were four rigids in the middle, so you could still pivot the cart on itself. And when we redid testing, we can now move this cart with a 40-pound max push force. So when the customer got this back, they said, well, we don't need to require four people to move this thing anymore. We can go with just one person. We know they can do it safely. And they calculated an ROI of less than 4 months just from the productivity savings of not having to bring over people every time they needed to move these, which they moved multiple times a shift. All right, so this one's slightly different on this cassette cart, 1,900 pounds. Again, a diamond style setup, but in this case, all the casters were in contact with the ground. So knowing that all casters are in contact with the ground, we know that the swivels are going to have the greatest impact on your push force. In this case, it was requiring over 80 pounds of force to get this to move, which you can see, I mean, you guys can tell me if that's good posture for pushing, but at 80 pounds, he's probably got to put most of his body weight into it. And in this case, they'd had multiple injuries a year for the last few years in these applications from this pushing motion. So again, so what did we do? So again, wheel designs. So we went with our split wheel setup, our Torgo setup. We went with our maintenance-free extended lead swivel sections that have optimized leads. And then in this case, because of the floor conditions, we said that green urethane isn't going to last. So we went with a tougher material that had slightly less slightly less rebound, but was going to be able to handle the potholes and debris and other things that were just inherent in that plant. It was an older facility. And what we were able to do here was reduce that push force about 56% and get it down to 35 pounds. And since they've implemented this, which they've had now for, I believe, 8 years, they haven't had an injury since. So they equate that to about $90,000 per year in savings.
From an injury cost
From
avoidance
an injury
standpoint.
cost avoidance,
Gotcha.
yep.
Gotcha.
And then this last one was a project we actually just finished 2 months ago. So this was moving hybrid batteries around an automotive assembly plant. And when they first designed the process, they designed it to move 3 layers of batteries, so about 12 batteries. And that weighed about 3,500 pounds. Well, very quickly they found out they're not going to be able to do this. It's not going to pass their push force. This company has the internal standard of 33 pounds of push force, and they weren't even close. So what they ended up doing was removing layers of batteries until they got to about 1,200 pounds, and now they met their push force. But the problem is that added over $1 million in extra logistic costs every year from not being able to stack those batteries as high as initially intended. So in this case, I mean, we had to go pretty extreme here. And again, they were using 8-inch wheels. We increased it to 12-inch wheels. We went to a dual swivel section. So this is what we call swivel on swivel. So we have two swivel sections that are stacked at a slight offset. So again, your total offset from your first swivel section to your wheels are still that optimal offset that we test for. But here, what because they also do a 90-degree test, and I can touch on that at the end. So that second degree of freedom in the swivel sections allows you to pass that 90-degree test. Then we knew we had to spread out and make that contact patch narrow. So we had dual split wheels. And they were able to modify their cart design to because this is a much taller caster. So they had to tuck it up inside the cart. But in the end, by doing all of this, they were able to reduce their push force down to 32 pounds. And now they're pushing the full 4 stacks of batteries. And they basically said this project paid for itself in like 2 weeks. So again, this is a case where casters were an afterthought, which they typically are. You get it out into production, it doesn't perform the way you want, and now you have all these other design constraints. Whereas if you worked with a caster manufacturer at the very beginning, you could have optimized that design from the get-go as opposed to getting something in, and now you're trying to piece a solution together with constraints that you've already built in.
So just to clarify, Doug, with that one, so the I guess that ROI or cost savings was primarily based around increased capacity and productivity, essentially,
Yep,
right?
yep, yep. So a good example too to show, you can be safe in your operation and you can still be very efficient and cost effective as well. So just to recap, when you're looking at caster designs, you got to look at the whole system. It's never just a wheel, it's never just a swivel section. It really is the whole caster system, even to the point of where you place the casters on the cart. So you want to pay attention to your swivel section design. You want to pay attention to your wheel design, also, the tread material, and how you're going to put these things on the cart. And if you guys leave here with anything today, and I'm not saying you need to work with us. I mean, there's plenty of other caster manufacturers out there, but make sure you're working with somebody that can walk you through these steps and help you pick something optimal as opposed to just letting a cart manufacturer pick something or picking, like, worst case, like pick something out of a Grainger catalog. No offense to Grainger, but don't just pick something. Take the extra time, work with an expert, get an optimized design, and your process will be much better for it. Like your people will be safer, it'll be much more efficient. And, we've never had somebody come back to us after working with us up front that said, wow, that was terrible. Everyone's like, wow, I never knew this thing could work so well. So don't think about casters last. Think about them, I won't say first, but somewhere in the middle.
And if I could add to that, and this has been great to understand all the details and the nitty gritty, but I think as everybody can see, there's a lot to it, right? And I think many safety professionals that our organization works with, or manufacturing engineers that we work with and train on, I think they feel like they have to know everything, to be able to spec out the right caster, the right wheel type, the right material, the right size, for all of their specific applications within their industry. And I always try to tell them this, and you can correct me if I'm wrong, but I'm pretty sure we're on the same page. Is these reputable caster companies, walk you through that process, and you just have to explain to them, the type of surface, right, that you're pushing on, the load, the total load weight that you're trying to move it, any height restrictions, vertical height restrictions or something. Sometimes things don't match up if you go to too high of a diameter. But again, a lot of these caster companies, the reputable ones will, are really good. And you guys, I think you do some testing even to really try to determine what is the optimal solution, before folks have to buy. So, I guess I just wanted to kind of
Yeah.
make that point. You don't have to know everything, right? If you know the right people to connect with and work with, they can help walk you guys through what's right for your specific application.
Yeah, yeah, definitely. And I'd say we've had a lot of companies over the last year, they'll actually send us a cart and let us do the testing so then they can figure out what the optimal solution is, as opposed to, just coming in the plant, taking a guess based on our best knowledge at the time. They'll actually send us one. We can do the testing. We send them a test report. That's worked out really well. And I think where it works out the best is, if we actually come and see the operation during that testing, because then you can evaluate the floors, you can evaluate the conditions that these casters have to work in. And just recently, we were doing a project with a large EV manufacturer, and we were doing this testing for them to optimize for a certain load. And then I got to their facility, looked at the conditions that these casters were going to be rolling in. I'm like, no, 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 we got to start over. Like these aren't going to work. So it's that combination of seeing, seeing the application and then being able to do the testing or have the database of results that I think help build that trust, with the end user. So with that's what I have. So I appreciate everybody listening, and I hope you learned something today that you didn't know.
Let's see. So again, f feel free to put some questions into the chat. We'll help facilitate those questions, and if I can answer them or Doug can answer them, we'll tag team this effort together. Give you guys a minute to type up your questions. Don't be shy. Don't worry. I guess just to get the ball rolling here, I guess I did want to ask. Because I was curious for my end, because a lot of companies that we work with, they just want, what's the total load limit, right? That they shouldn't exceed to put something on a cart, right? And I don't have a great answer for them typically. I know in the Eastman Kodak books, some of the ergonomic books that they had published, they had some total load weight restrictions in their studies, but I feel like casters have come a long way since those Kodak books came out. So I guess I was just kind of curious how do individual caster load ratings apply to their ergonomic performance? Are there any rules of thumb or tricks or tips that you guys can share?
Sure, sure. So that's a good question because if you look at like a caster catalog and say you want 1,000 pound caster, it's designed with certain safety factors in mind, but it's designed to carry 1,000 pounds, not necessarily the most ergonomically, but just to do it and not fail, right? Like have safety factors involved and whatnot. So that actually becomes quite tricky because, to get something to perform well ergonomically, normally you have to overbuild it almost. So say you only have 1,000 pound cart load and you're trying to move this and you think initially, well, I'm going to pick out a 250 pound caster because four of those is going to be 1,000 pounds. So I'd stop you there and say, unless everything is perfect, floors are flat, cart's perfectly flat, 3 points make a plane. So take your total load, divide by three. So now you're at 333 pounds. But really, if I want to optimize my push forces and really try to get those as low as possible, I really want to be looking at like 1,000 pound capacity caster. So now you might say, well, shoot, I have 3,000 pounds of capacity. Like, isn't that way too much caster for this application? No, if you're trying to get it to pass a push force to roll as easy as possible, because you do need that bigger wheel, you do need more premium materials. So what we've gone to is like we have guidelines of for cart loads up to say 1,200 pounds, here are the casters that you want to use. For cart loads up to 2,500 pounds, here's what you want to use. And I think that's helped people understand, Like if I'm trying to meet a certain push force, like I can't just pick a caster out of a catalog at a certain load rating. I really need like a system recommended to me.
Gotcha. Okay. Yeah, there's some questions coming in here. I don't know if you can see them too, Doug, or not, but maybe
Yep.
just this first one here comes in. Can you speak to whether you guys replace casters on material handling lifts, like not just carts? And I would assume maybe they're talking about material handling lifts, like lift carts or something like that, or not 100% sure what material handling lifts is referring to, but something that's mobile
Yeah,
that's also a lift. Do you guys do any of that, or do you guys replace wheels on anything besides just carts?
sure. Yeah. So like if it's like a man lift or something like that, like yes, we can replace wheels on that. Um, I mean, we do different conveyor rollers and things like that.
Okay,
So, I mean, because we make everything, I'll say yes, we can. And then using the
got
same design principles, we could make it roll easier.
gotcha. And then I got a question here from Paul. Can you better describe your testing practices? I guess when you guys are doing some of the testing inside your own facilities in terms of, load, pull force, longevity, is there
Yep.
a distance? Just I think there's some interest in that.
Yep. So we've actually developed a motorized solution to perform our push testing where we can set the acceleration to cover basically a certain distance in a certain amount of time. So we have certain customers that will dictate that to us. So we've based our standard around those.
Okay. So
Um,
the acceleration you mean is
yeah,
is
yeah,
set by
yeah.
the customer.
Because
Gotcha.
anybody that's performed push testing on a cart knows it is a highly variable test. And if you walk up and you push into it as hard as you can get a really high number. And if you walk up and just kind of gradually lean into it, you can get a much lower number. So if that's the only way you have to do it, I do think giving people a set distance to cover in a set amount of time, I think helps to prevent that from happening. And then I'd say make sure you're doing a proper, gauge R&R, repeatability and reproducibility study to try to take out that
Consistency.
variation from the different operators.
Right. Yeah,
So
force
best
for
case is have a motorized solution that controls everything so you get more consistent results. Um, and then on the manual side, just make sure you're taking enough readings across multiple operators to really take out those outliers.
but I know not everybody has that capability, right? To have a motorized solution like that.
Yep.
But sounds like you guys have that capability within your organization, is what I'm hearing.
Yes. Yep.
Okay. Yeah, force equals mass times acceleration. So that if that acceleration is so variable, then your forces are going to be all over the place. That's
Yep.
right.
And
Uh,
certainly, when you're testing against somebody else's casters and you walk up and you push as hard as you can, like it's one way to tilt the test in your favor, which is why we like the motorized solution as well.
right. Let's see here. So from Carl, so push force is a consideration to get a cart moving, right? To get this initial startup. Is there any design considerations to get a cart to stop, or is wheel friction sufficient?
No, so you have to take that into consideration as well. And that's why typically, like, we don't see applications going above 2,500 pounds. Like, even though we could get something heavier to like start safely, now you're trying to stop it. And if you have to stop it, say because something fell or somebody walked in your way, I mean, that creates a whole different set of forces on the body. And I don't think that's good for anybody long term either. So yeah, when the loads do get much higher, we do start looking at different braking systems and how you can utilize those to be able to stop that cart without having to use the human to stop it. So there's different, so like a popular style would be like a dead man brake system. So you have to engage handles to be able to start pushing, or else the brakes are engaged. So that way, once you get it moving and you need to slow it down, you can kind of let off the handles, the brakes apply, and you can slow the cart down gradually or in a case of emergency, you could just let it go and it would come to a stop.
And just I guess real quick, one thing that came up, at least in my mind, going back to your testing. I know when we're coaching, ergonomic teams and helping them, evaluate situations, we typically tell them to rotate to give you like a worst case situation for measuring an initial push pull force on a cart or whatever it is that they're moving. Typically we'll tell them to rotate the casters right 90 degrees to, if you have two swivel casters, right, rotate it
Yep.
90 degrees to the line of action that you're pushing. Is that, I guess, are we telling them the right thing, you feel like, or is that consistent with
Oh,
with what you guys do with your testing, or is 180 degrees better to give you a worst case? Just kind of wanted to chat about that, I guess, with the
yep.
expert.
Yep. 90 degrees will give you the highest push force.
Okay.
So we do have some customers that require 90 degrees. So typically when we do our testing, we do 90 and 180 just because there's a lot more manufacturers that go with 180. And that's primarily because to get those casters in that 90-degree setup is pretty difficult to do. So unless you have something built into your operation where those casters end up at 90 degrees all the time, for the most part, they're not, and they're going to rotate 180 pretty much every time. They're going to rotate 180. So that's why I think most manufacturers tend to go with that, just because it's the most common way that the
Okay.
casters move. But you do have the ones that say, okay, yes, this operation does have a lot of 90-degree moves, so we're going to test for it. Or you have companies that say, I want to be totally sure that this thing is safe, so we'll test at 90 degrees and it's still got to meet 33 pounds push force. So really, that really just depends upon
Yeah.
the company and their own internal standards. But 90 degrees will give you the highest forces.
So I guess we're telling them the most conservative approach.
Yep, yep.
Gotcha. Okay. I'm pretty much seeing. I think you answered Ernesto's question about how your company works with customers for assessing caster needs. So it sounds like you guys can
Yeah.
either come on site or they can send you some information or
Yeah, certainly
videos and
pictures. Yep,
yep,
pictures,
pictures and
videos help a lot,
design
if you're trying to
drawings
do
and
something
such.
quick. Yep.
Okay. I know that's probably variable based on, you know, uh, based on how much they want to put into it and what information that they have.
Yep.
But that's all I'm seeing come in. I know we're right at time here, and
Perfect.
I guess just real quickly, just wanted to share just to sum things up here. Oops, get into presentation mode. And again, feel free if you have additional questions, feel free to contact Doug at Caster Concepts, or if you have questions for us with the Ergonomics Center. Just wanted to say thank you guys. Thank everybody for joining us. And again, you feel free to reach out to us at the Ergo Center or ergocenter.ncsu.edu, or you can specifically reach out to me at jahoyle@ncsu.edu. But thanks again, guys, and hope you learned something. And we have recorded this, so we'll get this link out to you as soon as we can. Thanks again.
Yeah. Thanks for
Appreciate
having
it,
me.
Doug.
Appreciate it.